In this video, we want to take a look at the Laplace transform of a unit step function and one theorem about the Laplace transform of what you get when you multiply a function times a unit step function. So here we go. I'm going to take the Laplace transform of u sub c of t, and like any other function, how do you take the Laplace transform? You multiply it by this exponential, and then you integrate from minus 0 to infinity on t. Notice, though, that the unit step function is equal to 0 for all t less than c, and then it's equal to 1 afterwards. So when you're integrating from 0 to infinity, you don't really need the first bit. You don't need from 0 to c because u is 0 right here. So it really, things get exciting when you make it to c. So the integral I'm going to start at here is c. And once t is bigger than c, then u sub c of t is equal to 1. So this just looks like it disappears, but it becomes a 1 right there. And you're just integrating e to the minus st dt, which we can do. It's minus, there's a u substitution there, right? So you get minus 1 over s e to the minus st, and evaluate that between c and infinity. So you plug the infinity in, you plug the c in, and you subtract. Now, provided that s is a positive number here, this e to the minus infinity will be 0. So I need to make sure that s is bigger than 0. And I end up just with this part right here being e to the minus cs over s. So if this was u sub 2 of t, then I would have e to the minus 2s over s. In particular, if it's u sub 0, then this would just be e to the 0 over s, which is 1 over s, which is the same as the Laplace transform of 1, which brings up an interesting thing, right? U sub 0 is not equal to 1 on the negative side, but it is equal to 1 for all values of t greater than or equal to 0. And when we're doing Laplace transforms, we're doing the integral from 0 to infinity, so we're not really looking at the negative side. So at least on the positive side, u sub 0 of t actually is the same as the function 1, so it's good that we end up with the same value for the Laplace transform. Okay, now let's take a look at a theorem here. It says essentially, if little f of t has a Laplace transform, so if capital F of s exists for s bigger than a, some non-negative value a, and if c is a positive constant, then the Laplace transform of the unit step function at c times the shifted f function, so shift f by c, then that would be e to the minus cs times the Laplace transform of f unshifted, which there's another way of writing it. Let's just take a moment here to digest this before we read the last part of the theorem. F of t is some function. F of t minus c is that function shifted over by c. Right? When you multiply then by u sub c of t, you're saying, yeah, shift that function over, but don't even worry about it to start with. Once you get to c, then turn it on. Right? So you could look at the unshifted function starting at 0. It would look like something, and then you could shift it over and start it at c, and it would look the same, just shift it over. Okay, so this thing right here, inside the parentheses, is 0 up until you get to c, and then it looks like the shifted function f. And the Laplace transform of that is we're just saying take the Laplace transform of f and multiply it by this exponential e to the minus cs. And conversely, if f of t is the inverse Laplace transform of capital F of s, then the inverse Laplace transform of this exponential times f of s would be u sub c of t times f of t minus c, right? So if you are trying to take the Laplace transform, you can do it by this part of the theorem. If you're trying to do the inverse Laplace transform, you can do it by this part of the theorem here at the end. I will prove the first part, and I think the proof for the second part is essentially work this proof backwards. But how do you take the Laplace transform of a function? Well, you multiply that function times this exponential, and you integrate from 0 to infinity on the variable t. Now, what I'm going to do, oh, first of all, right, because this has got a u sub c of t in it, I don't have to worry about the values of t between 0 and c, because this function here is just a 0. And so I only need to worry about from c to infinity, and then those values of t, this u sub c of t is equal to 1. So it just kind of disappears. It doesn't completely disappear, it disappeared and changed that lower limit from a 0 to a c. And now I'm going to do essentially a u substitution, but I don't want to use the letter u because I'm already using it for other things, so I'll do a theta substitution here. I want to let theta equals t minus c, so d theta is dt. So the dt turns into a d theta, the t minus c turns into a theta, and the t over here would be theta plus c, so I've got a theta plus c that goes in there for that t up there. So then I can distribute the minus s in, and then notice that this could be rewritten as e to the minus s theta times e to the minus sc. But the e to the minus sc is all just a constant with respect to the variable theta, which is the variable that's being integrated here. So that can be just written out in front. Also, at the same time, I failed to notice that the c here went back to a 0. That was not by accident. That's not a typo, right? Because when c is equal, because this is the integral of t, so when t is equal to c, then theta is equal to c minus c, which would be 0. Likewise, the upper limit you might not have noticed, but it went from infinity to infinity minus c. Well, infinity minus c is still infinity. So this got shifted back down to a 0 because of that u substitution there with theta equals t minus c. So once I've got that out there, I'm now looking at the integral from 0 to infinity of e to the minus s theta f of theta d theta. Well, this is precisely the definition of the Laplace transform. And I'm going to write it as the Laplace transform of f of t, not of f of theta, because it doesn't matter. At this point, it doesn't matter what the variable is that's in there, whether you call it a t or a theta or a smiley face, right? It's a variable inside of a definite integral, and you're integrating from 0 to infinity. It's the Laplace transform of f of t. Okay? And this exponential ended up out in front. Let's do a couple of examples of that. Here is the Laplace transform of u2 of t times the sine of t minus 2. So I've got a shifted sine curve. The sine curve shifted over 2 and turned on at that point at 2. Right? So the Laplace transform, according to this theorem, would be e to the minus 2s times the Laplace transform of the sine of t unshifted. And we've done that in the homework, I think, or just look it up on the table. I know it's 1 over s squared plus 1. And so the Laplace transform of this thing would be e to the minus 2s over s squared plus 1. Another example I want to do is, I got a little more work here. This function we looked at in the previous video. It is, what is it? I had a u2 minus u5, and the whole thing times t. So it turns on at 2 and it shuts off at 5, but it's the function t in between those two. Okay. So that's the function that I want to take the Laplace transform of. Now, in order to do that, I want to rewrite this a little bit. So this is the way I had it, as t times that. But if I distribute the t in, I've got this and I've got that. Now, the theorem that we're using here says that if I'm taking the Laplace transform of a step function times another function, that this other function has to be written in terms of a shift of the amount, whatever that is right there, right? Because when we did this one, this was u2, but this was a sine of t minus 2. It's a shifted sine curve. So what I need to think of here is I need to think of this function t as a shifted something else, but shifted by an amount of 2. So what I'm going to do is I'm going to subtract 2 and add 2. So this t is now t minus 2 plus 2. And then I'll distribute the u2 in here in the following way, where I'll keep the t minus 2 grouped. and then I have a 2 right there. So this thing right here does look like a shifted t graph, but shifted by 2, and then times u2. So I'm going to be able to use the theorem on that. This is just a unit step function times a constant. I can do that. And likewise here with the t times u5, I'm thinking of the t now as being something shifted by 5. So it's t minus 5 plus 5. And so I can then distribute that in. I've got a t minus 5, and the minus sign is distributing in there as well. So it's a minus 5 u5. So now to take the Laplace transform of this function, that would be the same as taking the Laplace transform of all of this. This one right here, also no, what am I doing? The Laplace transform, maybe I've said this before, is a linear operator. So it distributes over addition and commutes with scalar multiplication. So I can take the Laplace transform of each of the 4 pieces, noticing here that this constant 2 comes out and that constant 5 comes out. Now, using the theorem that this is the Laplace transform of this is e to the minus 2s times the Laplace transform of the unshifted. This is just t shifted over 2, so unshifted would just be t. Then I have, well, the Laplace transform of u2 is e to the minus 2s over s. Likewise here, this is the function t shifted 5 multiplied by u5. So the Laplace transform of that would be e to the minus 5s times the Laplace transform of t, right? This is t shifted 5. This is t not shifted at all. And then minus the Laplace transform, 5 times the Laplace transform of u5, which would be e to the minus 5s over s. Now I can take the Laplace transform of t here and there, which is just 1 over s squared, 1 over s squared here, and a 1 over s squared there, leading to all of this. I got a common denominator, gathered some like terms together. Anyway, there is the Laplace transform of that little piecewise function that I had that was 0 and then t and then 0 again. Yeah. One more example. This example, let's go the other way. So let's do the inverse Laplace transform of something. So here I have I want the Laplace transform of 1 minus e to the minus 3s over s cubed. And I'm going to break this up, so use the distributive property to divide the s cubed into both of those pieces. Then the inverse Laplace transform is a linear operator, so it distributes over addition and commutes with scalar multiplication, so that minus sign can come out. So I've got the inverse Laplace transform of 1 over s cubed, and this, now the s cubes, when I go look in the table, I'm noticing that that's going to be related to t squared, and the formula is you need an n factorial on top and an s to the n plus 1 on the bottom. So with a 3 here, n is equal to 2, so I need a 2 factorial on top. So what I'm going to do is I'm going to multiply, sorry, there's a fly flying around here. I'm going to multiply by 2 and then multiply by a half and take the half out. Likewise, I'm going to need the same thing here. So I'm multiplying by 2 and taking the half out. That's all I did in this step. Now I can say this right here is the Laplace transform of t squared. So the inverse Laplace transform gives me t squared. And this one right here is the Laplace transform of t squared. So when I bring it back out, the inverse Laplace transform, so this is the second part of the theorem, this should be u3 times t squared shifted by 3, so t minus 3 squared. When I draw the graph of that, what you see here is it starts off as a parabola opening upwards. It starts off as this 1/2 t squared. But when it gets to 3, this turns on, and this t minus 3 squared, times a half turns on. And notice if you multiplied that out, you'd have a t squared minus 6t plus 9. But the t squared times, and all that is times minus a half. In particular, the t squared times minus a half is going to cancel out the t squared times minus a half that's already there. Sorry, t squared times positive a half. So those will cancel out. And what you'll just have is the linear and constant part of that, which is just a straight line. So this quadratic, this parabola that's opening upward, stops being a parabola right here and then is just a straight line for the rest of the time. And you can figure out that it's, what would it be, 6t minus 9 all divided by 2. So it would have slope 3 and just continue on up straight. Okay. So these are very different functions than what we've dealt with before because they're piecewise, but yet we can still take the Laplace transform of them. So in this video, we saw how shifting the function multiplied the Laplace transform by an exponential. In the next video, we want to look at what happens when you multiply the function by an exponential. It's quite interesting.